Now let's look at the Gauss Markov, the very well-known theorem about estimable functions. Uh, it has three components. The first component says that a unique unbiased linear estimator, let's say T naught prime y of Q prime B, exists such that T naught belongs to the vector space generated by the R columns of the design. And if T prime Y is an unbiased estimator uh, of Q prime B, remember we may have several linear functions of observations for an estimable function of parameters. So if there is another linear function of observations like t prime y, and it's an unbiased estimator of q prime b, then t naught is the projection of t on VR. Another thing, it has the smallest variance, so the variance of t prime not y is less than the variance of t prime y, and the equality of course holds if these two are equal to each other. Let me use the pointer. If t is equal to t naught, then the equality holds. And but what is this t naught prime y? So there exists a unique unbiased linear estimator which has the smallest variance. But what is that? In the third component, uh, it reveals this important things. The t naught prime y is actually q prime b hat, which b hat is any set of least squares estimator of the parameters. So if we have the least squares estimators of the parameters, then you can find this linear function of observations. And so q prime b hat is an unbiased estimator of q prime b, which has the smallest variance among all other linear function of observations. This is very important, and you see how least squares estimators are important now. You see now the importance, and let's look at the proof and see see how the uh, proof works here. Suppose that t prime y be any unbiased linear estimator. Since it's unbiased linear estimator, let us say a linear function of observations, the expected value is equal to q prime b. Now use the decomposition of t, and if you know the decomposition, you can start two orthogonal vectors. You can write t as t naught plus e, which t naught is in the VR, the vector space constructed by the columns, but are columns of x, and e, the vector which is orthogonal to t naught and belongs to the error space. Then, of course, the expected value of t naught prime y is equal to the expected value of t prime y, since the expected value of t prime e is equal to 0. So it is equal, according to the assumption, the expected value of t naught prime y is equal to q prime b. Therefore, we conclude that t prime naught prime y is an unbiased estimator of q prime b, and t naught is in VR. Suppose it also holds for another one, which is t1 prime y. We want to see whether there is a unique one or not. So the expected value of t naught prime y minus the expected value of t1 prime y is equal to, since these two are constant vectors, I can factorize it and bring it out of the expected value. So I can write it as t0 prime minus t1 prime the expected value of y. So an expected value of y is equal to xb, so I can write it as t0 minus t1 prime xb, which is equal to 0. So because both of them are equal to q prime b, remember why it is equal to 0? Because from left hand side you have q prime b. Remember, this one is another linear function of observation, which is unbiased. So minus q prime b, so you get this 0 from this part. Okay, therefore I can see that t naught minus t1 is in VE, the vector space orthogonal to VR. But t naught, we assume it is in VR, and t1 is also in VR. So the difference must be in VR. And we have these two, which we can conclude that t naught minus t1 is equal to 0 and t1 is equal to t naught. So there is a unique one. On the other hand, about the second component, the variance of t prime y, and if you remember the variance of let's say ax, suppose that we have a not necessarily x, let's say a z vector, and a is a matrix or vector of whatever, you can write it as the variance of z a prime. If it is even a matrix a z, then the matrix comes out again a capital A. You can write it even as capital A. So we can simply write it as t prime t sigma square. Why? Because the variance of y is equal to sigma square I. If you remember from the decomposition here, you can write it as t naught plus e. So I substitute it as t naught plus e prime t naught plus e. After simple algebra, you will get this equality. T naught prime t naught sigma square, e prime e sigma square, and then you will have a prime t naught sigma square and also t naught prime e sigma square. Since t naught is orthogonal to e, so t naught prime e is equal to e prime t naught equal to 0. And this guy is actually the variance of t naught prime t naught sigma square is the variance of this guy, and e prime e sigma square is the variance of this guy. And you see the variance is always non-negative, so we can conclude that the sum is at least variance t naught prime y. And so you see that the variance of t naught prime y is less than the variance of t prime y. So it shows that the unique one has the smallest variance. What about the third component? The expected value of, let's look at the third component, which shows the importance of the least square estimators. It says that this linear function of observations is nothing than q prime b hat. B hat is the least square estimators. So you take this vector of coefficients and multiply it with b hat. Now let's look at the proof of that. The expected value of t naught prime y is equal to t naught prime expected value of y, which is xb, and it is estimable function, and q prime b is estimable function, so it is an unbiased estimator for q prime b. So these are equal to each other. And it was actually the implication of the previous theorem. So we can write q prime as t naught prime x. So we had it already, but we repeat it here again. But t naught prime y minus xb hat is equal to 0, because this belongs to VE. If you remember from the projection, if I have y and I consider the projection on V. Suppose this is the VR space. If I consider the projection, this is xb hat or x beta hat, not difference, and this is the orthogonal vector to x beta hat or b hat. This vector. So since this belongs to, let me write it in another color, to VE. If I write it to another color, this y minus this vector y minus x b hat belongs to VE. So we can conclude that T0 prime is in VR. VR is orthogonal to VE. So we can conclude that T naught prime y minus xb hat is equal to 0. Therefore, from this equality, T naught prime y is equal to T naught prime xb hat. And it is indeed, according, if I replace this one, let me use another color in order to better show it. If I use this guy here, so I can, instead of T naught prime x, I can write Q prime, and you see this T naught prime y is equal to Q prime b hat. So one way is proved. In order to prove the other way, the estimated Q prime b hat or T naught prime y is called the best estimator of Q prime b. This is an let's say important statement. We call it best linear unbiased estimator. Unbiased estimator. And or you may see in other contexts it is also abbreviated with blue. So if you see blue about estimable function, it means that linear function of the elements of the least square estimator. Conversely, let's look at the converse for the proof. Conversely, for any d in VR, d prime y is the best estimator of the estimable linear function. So the expected value of d prime y is equal to d prime xb. Because d is constant, it comes out from the expected value, and the expected value of y is equal to xb. Therefore, VR is called the estimation space. Sometimes the regression space. Not always estimation space. And this linear set, the T prime y, which with T belonging to VR, is called the estimation set or regression set. You can also say regression set. In it, the total of sum of square, which is equal to y prime y, can be decomposed as SSR plus SSE, the sum of the squares of estimation or regression plus the sum of the square of error. And the sum of the square of regression can be easily obtained by b hat prime x b hat. And it is y prime y minus SSE. Further, suppose that the columns of the error space n times n minus r. Remember the rank of VR is equal to r here. So the rank of VE is equal to n minus r because the total rank is equal to n. You can write the SSE as y prime e prime e inverse e prime y. So if the columns of E generate VE, then you can write SSE as by this formula. And subsequently, the expected value is equal to n minus r sigma squared, and SSE divided by n minus r gives sigma squared, which is an unbiased estimator of sigma squared. So you can simply divide it by n minus r and get an unbiased estimator for sigma squared. So better say 1 over n minus r SSE is an unbiased estimator for sigma squared. Okay. We also have another theorem, which is very connected to the previous one, which I'm going to explain in another video.